All right. Well, I came here to do lectures and drink tea, and I'm all out of tea. So let's get going. Lecture 16, Part 3. What are we talking about? We're talking about rotational motion and things rolling around and torques and all of those fun things. So when you have rotational motion, then we have energy. And what's the first type of energy that you're going to have? When we always roll out energy, what do we talk about? We talk about work first. Okay? And work is equal to some force. How do I want to, let's actually call it a force. And we're going to multiply that by some distance. Okay, but when something is rolling around, man, it's so much harder to draw a circle. I'm almost good at it. When something is rolling around, consider this thing rolling from here to here. And so then this is the distance that gets covered. What do we call that? We call that delta S. It's still a linear distance, right? So x equals delta S. That's fine. Our force is equal to this work. So let's write out distance here. All right, so we got force times distance equals our work. Well, we're rotating with some radius r. And we've got this x equals delta S, and that's our distance. So our work is equal to the force of us pushing in this direction, force, times the delta S around our nice circle, whatever it is. It could be a rod, or it could be a disc, or whatever, but something that's rotating, doesn't matter. So if I decide, you know what, I can multiply R times my force, but then I have to divide my S by R if I'm going to do that. But let's say we do. All right. Well, look, right here, what is this? Of course, R and F are perpendicular to each other, so that's nice. That's our torque, right? And delta S over R, what is that? Well, x over r equals theta. So that's theta. So really, our work is equal to our torque times theta. And it's the same type of equation. So we can go back up to our rotational equations way back when I started doing this, our rotational equations, and we can write down our work is equal to our torque times theta. On this side, our work is equal to our force times our distance. So there you have it. With this one has theta equals 0. This one doesn't need one because the torque is in the same direction and all that, blah, 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 blah. Okay, so we've got work equals torque times theta, and work equals force times distance. So let's come back down here and keep this party started, keep this party rolling. So this is rotational work, okay? So rotational work. All right. Now we can do a couple of things. Of course, our, let's say our, here, I'm going to delete that F. I want to put an F exactly, I want to put an F exactly in the right spot. Okay? So, if we apply a force at this point, totally perpendicular to our radius r, tangential, right, to the radius, to the surface, then that means our delta S is going to grow this direction. We also will have an increasing acceleration because that's the direction of our angular acceleration. All right, so everything's perpendicular. We're all happy with all the perps. So let's look at our torque being I alpha. That is our torque net, of course, but we've only got the one force anyway. So we can insert that. So we now have I alpha theta. Okay. And I don't know if you guys remember, but this bit right here is very similar to what we have when we do our omega squared is equal to omega initial squared plus 2 alpha theta. Right? It's our delta theta. Well, that thing means all the rest of this equation can fit in there. Okay? And everybody's like, ugh, gross. But let's do it anyway. So alpha theta is going to equal our omega squared, our omega final squared, minus our omega initial squared. And we're going to divide all that by 2. Nice. I'm gonna do that instead. Okay. So our work net, I don't like this omega here. It's too much like work. It's not work, it's an omega. So our work net is now equal to our moment of inertia times our work final squared minus our work initial squared over 2. We can break this up, right? We can say that our work net is equal to 1/2 I omega final squared. And we can say 1/2 I omega initial squared. Oh boy, what does that look like? This looks like we've got our work net is equal to something very similar to KE. In fact, this is rotational kinetic energy. All right? And this would be our kinetic energy initial. So we've got initial kinetic energy and a final kinetic energy, and we're subtracting the initial from it. So that means we now have, let's just do it like that. And so that means we now have delta KE. Does anyone, and I'll put a little rotational on that. Is anyone surprised? Okay. And also, this is our work energy theorem. Okay. A rehash of the work energy theorem. And it's the same thing, only now our kinetic energies are done with the moment of inertia times the angular velocity squared. All right, so angular velocity squared times your moment of inertia divided by 2 is your kinetic energy. So lock that in. All right, we got to lock these ones that I put in here that are square, boxed. All right, box them in. Okay, good. Before we go, let me just write a little rotational on that, all right? Because it's definitely rotational kinetic energy. So what do we have? We now, should I scroll back up there? All right, I'm gonna scroll back up there. Add to your list. Add to the list. We got more stuff to put on the list. I'm gonna just put it in there that this is also delta KE, and we haven't gotten to the momentum thing yet, so I'm leaving a little space there, but I need to erase some, so we're going to erase this structural line. We've already done this, so who cares about that. Give ourselves some space here. Okay, so let's move up a little bit more. Erase a little bit more. It's not as fast as the eraser on the whiteboard, but it's close. Okay, let's do it. So we've got delta KE. However, what is our new KE? KE over on this side is 1/2 mv squared. That's our linear KE. Our rotational, we can write linear. Our rotational KE is 1/2 I omega squared. Same stuff, just different ways of looking at it, okay? And if you notice, you can do a unit analysis. I recommend you do a unit analysis. Of course, over here we've got joules because we've got meters kilograms times meters squared per second squared. And on the other side, we've got so I think they just closed all the campuses for tomorrow. I just got the note. All right, so you're probably not going in anyway, so don't worry about that. Anyway, you'll also have joules over here. How does that work? Well, our I is in kilogram meters squared. Our omega is in radians per second, so that's radians squared per second squared, but the ghost of radians goes away, so we're left with kilograms meters squared per second squared. That's a joule. So either way, we've got joules, okay? So excellent, good job by you. All right, let's move on down. get on back down to where we were at with our work energy theorem. All right, so let's do an example. And here's what I'm going to do. I'm going to lay out the example, all right? And I'll say, all right, now hit pause. And then you guys hit pause. And then you do it. And then I'm going to show the solution, okay? All right. So here we go. Do you guys remember turntables? Maybe. Some of you might. Turntable is a record player. Okay, so we've got this box, and there's this arm, and it reaches out, and the record spins around, and a little needle bounces up and down and vibrates, and that vibration gets amplified and turns it into beautiful music. All right, well, turntables have 2 speeds, all right? 2-speed turntables. Depending on what kind of record you put on there. So there's LPs and EPs. Or maybe LPs are equal to EPs. It's been a long time. I don't remember. There's also I don't remember. I'm going to give up on that. Don't worry about extra long plays and all that. I'm going to say there's 2 speeds. So omega could equal 33 RPM. Okay, that was one of the speeds. So let's do omega 1 there. And then omega 2 was 72 RPM. So one was recorded at 72 and one was recorded at 33. And then what was fun was you could play the 33s at 72 and it was really fun, right? Because it's twice the speed. Or more than twice the speed. So that was fun. Okay. So the first thing we want to do is convert. Now, we're not going to deal with omega 2. So let's just call omega. Keep it simple. We're not going to deal with that. Maybe I should have you, after we do this, do it again with 72. Maybe. We'll see. So here's the thing. We're starting out, omega initial is going to be 0, right? Because it's sitting there. It's not spinning yet, right? So you start out at omega equals 0. And then you accelerate with some alpha, and you get up to omega final equals 33 RPM. Now we still need to convert, right? We got to convert 33 RPM. So we're going to multiply that by, it's revolutions per minute. So first of all, we got to get rid of the minutes, right? So 1 minute divided by 60 seconds, that'll give us per second. And now we got to get rid of the revolutions. So we've got 2 pi radians. And we're going to divide that out by 1 revolution. So that gets rid of our R. We've got rid of our M. The per, that's just our per. That's this line, right? RPM. So this should give us a good, let's say it's equal to something, 3.45 rads per second. All right, radians per second. So instead of writing it in terms of RPM, I'm going to write it in terms of 3.45 radians per second. Good. All right. Now we're also given I. Our moment of inertia, I, is 6 times 10 to the minus 3 kilograms meters squared. Good. Now, here's the question. What is delta K E rotational? All right. So you guys can pause it anytime you want, and pause, get it right, do your thing, and then come back in a second after you pause. Here we go. We want to do KE initial and KE final. KE final is going to be equal to our 1/2 I doesn't change, just like mass doesn't change, omega final squared. So instead of putting omega final squared, I'm going to put 3.45 radian per second, and I'm going to square that. And I could stick in what our I is there too, I suppose, but I'm not going to do it. And there is our, initially, our omega is 0. Whether it's in radians or revs per second, it's still 0, 0, 0. So we don't have to subtract off anything. And we'll have, once we get this, we'll have our delta KE rotational because of the 0. So, yeah. All right. I want to move up just a little bit. So plugging all those numbers in, we get KE, delta KE rotational is equal to 3.6 times 10 to the minus 2 joules. Hopefully that's the answer you guys got. And everybody will be happy. All right, so all right, what is it that I want to know? Okay, so we've got this turntable. I'm going to reanalyze the turntable. Let's look at the circle that is the turntable. And we start our rotation here. Okay, so this is the point that we're going to watch. And the acceleration happens as it goes from this angle all the way around to this angle. That's the only time it's going to have an acceleration. All right. Also, the radius that we're dealing with here is r, and r is equal to 20 centimeters. So we can rewrite that. I don't even know why I wrote it like 20 centimeters, because that's 0.2 meters. Okay, and it's going to rotate and it's going to accelerate. So by the time it starts out here at omega 0, and by the time it gets to here, it's full on accelerated completely. We want to know, here's the question, and pause anytime you feel like you can pause it and get the right answer. So what is the force applied to do this? Okay? What is the force applied? Now keep in mind, we're talking about a force that is going to be applied totally tangential to the radius, all right, to the surface of the circle, circumference. Totally, all right. And what are we dealing with? With theta. So what is theta? Let's find out what theta is just real quick. We're going to be going all the way from here to here. That's 3/4 of 2 pi. All right. So this is a preliminary thing. What is theta? This is the question. All right. So that's the one you want to try and get. But what is theta? It's 3/4 of 2 pi. Well, that's simple. It's 3/2 pi. Okay. That makes sense. So, what is 3/2 pi? Theta. But now you can take pi, multiply by 3, divide by 2, and you'll end up with 4.71 radians. And that's how you want it. You want it in radians, okay? So keep your calculator, though, in regular mode. Just use radians. No switching to radian mode. So, cool thing happened along the way to the bank. We have work net is equal to R times F times F net times theta. Oh boy, where did I get that from? Well, I got that from up above. Do you guys want to see it? Right in here. Right in here. Okay, so what did I do? I set this equal to R times my F times my theta. Okay, bingo. So let's go on back down. R times F times theta. Good. And that's also equal to my delta K. Well, that's not a K. Let's get a K in there. KE rotational. And that's a number, right? So I know that. So I can solve this because I know what theta is. I know what R is. Let's rewrite R is equal to 0.2 meters. So I know that and I know that, and good. So my force net is equal to my delta KE rotational divided by my R theta. And I can put those numbers in, 3.6 times 10 to the minus 2 joules, and we're going to divide by 0.2 times 4.71. This whole thing, believe it or not, I'm going to even get rid of the joules here. You can go through, prove it to yourself, but you end up with newtons. All right? So you get newtons. It's a newton meter per meter, which is a newton. That's essentially what you get. Newton meter per meter, and that's a newton. So, fine. That's a number. What is that number? That number is equal to 3.8 times 10 to the minus 2 newtons. So the force doesn't have to be very big. We've got a small moment of inertia, and this will get our record player up to speed in 3/4 of a turn. Very nice. Okay, and you probably never paused to try and figure it out. Oh, maybe you did. I hope you did. Okay. So look at example 10.9 in the book. That's the thing I have written here. Okay, well, I'm going to just say the same thing. I don't even remember what example 10.9 in the book is. Example 10.9 in the book. And maybe you had homeworks that helped you with that. Probably. Hopefully you did. And we're gonna do example 10.10. So let's do example 10.10. We want to calculate the speed of a rolling cylinder going down an incline. All right. So here's our incline. Here's our angle theta. I'm going to draw a cylinder here. Good luck. And this thing is going to roll down with some velocity. It'll roll down with also an angular velocity. And both of them are going to accelerate. So we've got an acceleration. We've got angular acceleration. So all kinds of stuff are happening, all because of gravity. And I'm going to give you two things. Here's one can, and here's another can. Okay, so we've got these two cans, and one is got a larger radius. R2 is bigger than R1. All right, and we're going to roll these cans down the hill, and we're going to try and figure out which one goes faster. So which can is faster? Okay, awesome. So here's the thing. We've got so much potential energy, and of course we want to know what their final velocity, V final, is down here at the bottom. Let's start analyzing this situation, but we're going to use conservation of energy. So what is our potential energy initially? Well, we've got some height that this thing is at. So our potential energy is mgh. We all know that. And we're going to set that equal because that's our initial energy. And we've got some energy final. So I could say energy initial. And what are we dealing with? Friction? How are we dealing with friction? No friction. Okay? We've got enough rotational energy taking things away, so we're not going to worry about that. Our final energy final. Well, we're not going to have any more potential energy. So our height is now 0, and that's going to be out. So all we're going to have finally is rotational kinetic energy and linear kinetic energy. So we've got linear and rotational. And you guys know which one's which, right? Rotationally, 1/2 I omega squared. Linearly, 1/2 mv squared. And I'm going to put a little final on there. In fact, we could put final here too. Good. So energy final, and this equals our energy initial, so I'm going to write mgh right there. Convenient. What if instead of I, we write out, so I've got 1/2. Instead of I, we're going to write it out. What is I for a rolling cylinder along a certain axis right down the middle? Okay, so we've got this axis right down the middle. It's got some radius r. And what is the I for that? You can go look it up. Please do. And you'll come back and you'll say, oh, that's just this. So fine, I'm going to insert what that I is. I'm going to say 1/2 m r squared. And then I'm going to multiply by omega final squared. And then I'm going to come over here and I'm going to say 1/2 m v final squared. And all that equals mgh. So far, so good. M's. We've got one in each, so the M's are gone. Nice, good for us. And we can say GH is now equal to 1/2. I'm going to move this one first. So 1/2 V final squared. And then we're going to work with our 1/2, let's call it a 1/4, r squared omega final squared. Do you guys remember what r omega, oh gosh, r times omega is? R does not equal omega. R times omega, what is that equal to? Take your time, put pause, whatever you want to do, figure that out, and then you'll notice that it's equal to velocity. So if we've got r omega final squared, both of them are squared, we've got velocity squared. So I'm going to delete this and say that this is our final velocity squared. And if we add those two things together, we've got 1/2 plus 1/4, that's 3/4. And V final squared. So GH equals 1/2 V final squared. Okay? And so far so good. I'm going to move up. We need a little bit more space. And I can now solve this equals this. So let's just put GH here. We're going to solve this one right here for V final squared. I've got 4GH over 3 square root equals V final. So we can go back to which one of these guys is going to go faster, the R1 or R2, and we're going to note that R is nowhere to be seen. R, not here. Not here. So if R is not here, R is not a variable that this V final is dependent on. It has no difference. We could have a big can or a little can or whatever. It doesn't matter. As long as they have the same moments of inertia, we're going to have the same speed. So that's the key, though. Okay? Moments of inertia. We've got to have same moments of inertia. All right? So let's do an example. I want you guys to do an example. How are we doing on time? Let's do this example and then if I do this example, what do I have after that? I've got one more after that. So let's do this quick example and we'll get to the next thing. So here's an example. I've got my can on some slopety slope. There's a theta going on. My can has a certain height. And it's, of course, going to have some omega going like this because that's how it's accelerating down the road. Also, what's happening? What's our friction? What's our friction doing? Our friction is static friction. So it's not sliding, it's rolling. Okay, so mu static is holding this. Every single time it's touching, it's holding it in place and spinning this thing around. That's where the extra energy goes in to that. So, all right, let's give ourselves some numbers. Height, 2 meters. Mass, can. Solid disc, whatever. Not 7. Let's do 3/4 of a kilogram, and we'll say that it's yeah, that seems fine. Okay. Question to you. What is the final velocity? Pause it, come up with what the final velocity is, and then unpause because I'm going to do it right now. What is the final velocity? We solved it. We already solved it. All we have to do is say 2 times GH over 3 square root, and simple math, and we end up with 5.11 meters per second. That's our V final. We'll box that in, and we're golden. I think now's a good time to take a break. So I'm going to stop and we'll come back with, what are we on? Part 4? I think we're on part 4. So we'll come back for lecture 16, part 4. Is it part 4 already? I don't know. Okay, I'll change it if it isn't. Okay, bye.